All right, welcome back. Third time's the charm. Let's get into the nitty-gritty of training. So, if you remember when we talked about the nature of the decision stump, that it's an exhaustive search. So when we get large numbers of possible dimensions, we know that this can get pretty hairy, okay? So when we expand the idea of an exhaustive search into a tree where we have to search all the features for all the different decision points, and we can rearrange any one of those stumps in any order to make a tree, we can see that we get very big numbers very quickly with the number of features. Okay, so it can be shown theoretically that learning the absolute simplest, smallest tree representation is an NP complete problem. So that means that it is going to take a non-deterministic computer to do it in polynomial time, NP complete. Again, if you have not had a computational complexity course yet, or are not familiar with the big O notations and stuff like that, this may not make much sense. But let me summarize it for you, that means that these algorithms are among the hardest to do when the number of dimensions get big. Okay, so because exhaustive search is annoying that way, that it adds a few extra n squares to the problem, then let's not do that. Let's do greedy search instead. In a greedy search, what we're going to do is we're going to, at every decision point, we're going to make the greedy choice. We're going to take the stump that looks the best to us and add it to the tree as a decision point. Okay? So we don't have to go back and check again and reorder previous choices based upon the choices we're making now, right? We're only going to make one choice as we go through the path of constructing the tree, and that makes things a lot nicer. So the basic algorithm in pseudocode looks like this. Okay? Remember, this is a recursive algorithm. So we're going to call this algorithm with a set of training examples, a set of attributes or features, and don't worry about default, okay? But fundamentally what we're doing is we have up here this stuff actually. These are all the special cases. These are what happens when we run out of training samples where we've seen them all. It's what happens when we run out of features to split on. It's what happens when we are done, essentially, and our various stop conditions. So different algorithms for decision trees will change what's up here, okay? These are handling the special cases. But the vast majority of making a decision tree is right here, okay? This is the recursion. So what we have to do is we have to use some sort of function to choose right now how to split, okay? So given our data set of features and samples, it chooses our best possible attribute, our best possible feature to split on. Okay, we make a new tree with its root at best, and for each value of subdivision of best, right? So for the weather outlook being overcast or sunny or rainy, those are the three possible values of the attribute outlook, weather outlook. Okay, we're going to split up the examples and make a subtree that goes on from each one of those branches. Okay, and in that subtree, we're going to call our algorithm recursively with everything on the sunny branch. Okay, and then again, we're going to do it again with the next thing, which is the cloudy branch. Okay. Yeah, voila, at the end, we return a tree as we are returning out. So there are many different kinds of algorithms for doing decision trees. They differ in these features, okay, in the kinds of attributes it can handle. Can it only handle discrete tasks like Boolean kinds of logic operations, or can it handle continuous numbers? Okay. it differs in how it chooses that best attribute. That choose attribute function is a key difference between different algos. All right? And they do different things to stop building the tree. Okay, so those if statements that I was talking about in the beginning. And when those if statements are handled right, they can be a form of regularization, preventing the tree from overfitting the data. And I'll show you exactly how that works. So all discussions of decision trees start with ID3. ID3 is one of the earliest algorithms and certainly the first algorithm that actually was any good. It's due to J.R. Quinlan, and it is a Boolean-only algorithm. It's only going to operate on discrete logic things. Okay? So you can operate on predicting classes from classes, but you can't operate on predicting classes from continuous real-valued numbers. So it doesn't do any special early stopping to prevent overfitting, and it makes these trees that are kind of bushy. They're short, they don't have a lot of levels to them, and they get pretty wide, therefore. So here is how you choose an attribute. Okay? So this is called an information gain. Right? And what happens is that we partition every time we partition, right? So we're at Outlook, and we are partitioning Outlook into sun, wind, and rain. So those are S1, S2, and S3. Oh, I put it behind my head. Good job, Jason. All right, but you get the idea because you saw S1. Okay, so this sum is over the t different values that come out of this node. This term here, that's just the number of data points that are going through this that belong to the sun. Okay, so S of I is the first time around, that's S1, and that is just how many sunny data points we have going through the system. Okay, over the total number of data points going through the system, the total number of size of the training set. Okay, what are these mysterious terms here? That is, I is for information. So it's for an information metric. And it's something called Shannon information. And we're going to discuss that right now, exactly what that is. What I do want to say is that when 1986 they wrote this, I for information was a reasonable thing to write. Nowadays, we don't use that notation. We replace it with H. So I have just, hopefully you saw it change. You didn't get some change blindness on you. So these are H's now, not I's. Right? So I want to do that to make it consistent with modern ways that we do this notation. Right, so that gain function is something that we're maximizing. Okay, we want to choose the partition that maximizes that gain function. I know we're used to minimizing loss functions, but this time we're maximizing. And right, that's no big deal, because all you have to do to convert from one to the other is add a negative sign on the front. So if we wanted to do minimization, all I had to do was put a minus sign in front of that G. And now we can do minimization, okay? So that Shannon information, that is also called entropy. So what is entropy? Entropy is essentially uncertainty, okay? If you're very, very certain, you have low entropy. If you're very uncertain, you have high entropy. So let's look at these three distributions here, A, B, and C, okay? And consider that as the idea that it's encoding the probability of a variable y being a certain value once you know that variable x has a certain value, okay? So which one of these has the lowest uncertainty? A, B, and C. which one, if you're going to roll the dice and come up with an X value, which one would you be the most certain about what it's going to do? Lowest uncertainty, the most certain that before you see the roll of the dice that you know what's going to happen. Anybody? Yes, Leo Messi. Very good. I'm impressed that a footballer of your caliber is also so good at information theory. You're correct. It is indeed A. Okay? So A is the least uncertain because, why? Because more of the probability mass is over here. And so we're pretty sure that any new sample that comes in is probably going to land in that probability mass. Okay? This one has the highest entropy. It's the most uncertain. We have no idea where a new sample is going to land, anywhere in there. This one, it's more likely to land in here than it is out here, right? So this one's in the middle. This one has the highest. This one has the lowest entropy. All right, let's make this mathematically formal. So for discrete random variables, we can define the Shannon entropy as the summation for all the data points. Okay, that's what we're doing here. It's a summation of all the data. So the probability that a given variable x is equal to a certain value, whether that's, you know, wherever we were on that x value that we want to test for, we're going to, sorry, man, this is my bad. This is not over data samples. Good job, Jason. All right, this is, of course, over the possible values of x. So right now, again, we're restricting x to be a discrete random variable. So x takes on m possible things. So this is from I equal to 0 to m. Okay, so if there's m possible values that we can take on with this. So we're testing the probability that we get a particular variable multiplied by the log of that same probability. Okay, I don't want to get into deriving exactly what this means and why it is like that, but please trust me that that is the definition of the entropy of a distribution. And you can take it into the continuous case by just turning that summation into an integral. Okay, so what if we had binary variables? Okay, that means that I could just take one of two possible answers, a 0 or a 1. Okay, so if this is x of I equals to 0, and this is x of I is equal to 1, okay, if each outcome is equally likely, this is a coin, which is fair, and we flip the coin and it's a 50-50 chance it lands heads or tails, then we just run forward in this calculation that this is the probability of heads, and this is the probability of tails. Okay, so each one of them is 50-50. We calculate the h. I shouldn't have used h for heads there. Okay, so the entropy of heads, the entropy of tails, they are the same because they're 50-50, and that gets us an answer for how much entropy is in that discrete random variable. Okay, what does it look like if we have a 90-10 split, where 90% of the time the coin lands heads? It's a bent coin. It's a cheater's coin. Okay, and if you know how to make it work, you get 90% heads out of it. Well, in that case, our entropy is much lower. Okay, it's 0.14. It's less than half of the numeric value of the fair coin. Now remember what we called entropy. We called entropy uncertainty, right? Because the coin is bent, because it lands heads almost all the time, we are not uncertain about what the answer is going to be when we flip this. So this is exactly what we want. Okay, and if we go the other way, if it's a 90% tails coin, we get the same entropy, okay? Because we have the same uncertainty. It's just whether it's going to land heads or tails, and we don't care about that. What we care about is knowing the coin, what are we likely to see on the next flip, okay? So bent coins have low uncertainty, and they therefore have low entropy. Perfectly balanced coins that are 50-50, they have high entropy. They have a lot of uncertainty about what's going to happen next. Also, some people call entropy surprise, right? How surprised am I going to be to find out the answer? Okay, we're going to introduce two more concepts from information theory. So what we had just a minute ago was we had just done h of x, just of one discrete random variable. Okay, but what if we have two variables and we wonder, how related are these variables? Well, this is called the joint entropy. In other words, this is the entropy of x and y together. Okay, whatever the x and y's are, whatever the variables are coming out, this is the entropy of x and y, the joint entropy. So it looks exactly like we saw a minute ago, except this time we have two terms inside the probability. It's x and y. Big surprise. Okay, other than that, it's exactly the same. So here we have two variables. Okay, we have x. Take each one of them is binary. Okay, so they can take two values. And what you're seeing inside the table is this is the probability that x equals x1 and y is equal to y1. Oh my goodness. y1. That's supposed to be a number 1. Okay. So these four squares sum to 1 because they're probabilities. And what is happening here? Well, so 2/10 of the time, whatever our two variables are, they land on 1 and 1. Maybe these are, two coins that we're flipping. Okay? So what's the probability they both come up heads? All right, it's 0.2. All right, and because we have that probability, we can calculate that value right there. Right, so there's a continuous version of the same task, and as you can see, we can, oops, get out of my way. We can calculate those values. Okay, that's good enough at this point, you can see. Right, so this is just the chain of calculating that point, calculating that point, and lastly this one. Okay, sum them all together and you get the entropy of the joint distribution x and y. Okay, critical here is to realize these negative signs. I cannot tell you, it seems like every third time I try to calculate entropy of something, I somehow leave the negative sign off. Don't forget that. Oh, and by the way, why is that negative sign there? Because the values come out negative when you do logs of small numbers, right? The log of something less than 1, which a probability is going to be less than 1, right? So the log of something less than 1 is negative. So to get entropy to be a positive measure, you need to throw a negative on the front. And in fact, by the way, there's an equivalent formulation here where you could also have probability of xy log 1 over probability of xy is also equal to h of xy. And note this one doesn't have the negative sign. Why? Because we pulled the negative sign out from here. So the log of an inverse, we can pull the negative sign out and put it to the front, right? Okay, just a little FYI there. Okay, so entropy measures the amount of uncertainty for a probability distribution x, or how value would be for you to know x in order to know the probability of x. Okay, so the once again, peaky distributions, right, where most of the probability mass is in one place, have low entropy. Flat distributions have high entropy. Okay, the last two things I'm going to show you is we now need to calculate, we did the joint, right? So for those of you that are familiar with conditional probability, since we did joint probability, you might guess that we're going to do conditional probability. We're going to do conditional entropy. So this is the entropy of y once you know x. So if x lets you predict y, then you're not going to be very surprised. Once you know x, you will probably know y if y is easily predicted from x. Okay? So this is a key term, right? So once again, this is exactly just like everything else. It's the probability times the log of the same probability. It's just that now these probabilities are conditional probabilities. They're probability of y given x. Okay, so here is our same data set that we've already had. So if we want to know the probability that y is equal to 1 given x is equal to 1, well, that is 0.2 over everything else, right? And in this case, everything else is, we're conditioned on x being 1, so it's over this, so it's 0.2 over 0.55, right? It's the 3.5 plus the 2. So that, my friends, apparently is 0.36. I'll just believe what the slide says because doing that in my head ain't going to happen. Okay? So the probability that y is equal to 2 given x is equal to 1 is also going to be over 0.55 because it's in the same column, but the numerator is going to be 0.35. Okay, and apparently that's 0.64. All right, so these are the conditional probabilities built from this truth table. Okay, so now we can calculate using those probabilities, those conditional probabilities, we can now calculate the entropy of the joint. Entropy of the conditional. Probability of the entropy of y, given that we know x is equal to 1. Okay? So that number is a number, 0.66. You can work that out yourself in your own time. And we can do that again for y given x is equal to 2. Right? So for each one of these possibilities, 1, 1, 1, 2, 2, 1, 2, 2, we're going to work this out. And in the end, we're going to have the whole conditional entropy is all those numbers added together. Okay, so again, think of conditional information as being how much information you've gained about y once you know the value of x. So let's look at the relationships between all these, okay? So the joint probability, the probability of x and y, you can break that up into probabilities of x, the probability of y, and the conditionals, okay? And it's the same with information. Information is exactly the same way. So what happens here is the entropy, the information in both of these is a summation of the entropy of each one separately, and there's some overlap between them. And that overlap is this thing that's called the mutual information. Okay? So the joint is always equal to any one of them plus the conditioned on that one, right? So h of x comma y is equal to h of x plus h of y given x, or it's equal to h of y plus h of x given y. But if x and y, if their entropies overlap, right, if they're not completely independent, then there is some sort of mutual information. There's some sort of ability that we have to predict these two given each other. All right. So this last part, the mutual information, is the distance between the joint and the product. Okay? And so we can write that down this way. Okay, so I've just kind of done a high-level overview of all this. I am well aware of the fact that it takes more than 15 minutes to learn information theory. If this is your first time at this rodeo, please don't worry. Let me tell you why. A, there's no more exams, okay? And you're not going to have to know this right off the top of your head. However, I do want to let you know that this kind of information theory is a useful tool in the rest of machine learning. So it is definitely worth your while to start to learn it. I highly recommend starting with what we just did, but in better detail in Chapter 8 of the David Mackay book, which is available freely online. And that whole book it's a machine learning book, but it doesn't start with any machine learning. It has like 10 plus chapters before it gets to any machine learning. And it's all about understanding inference using Bayesian and information theory kinds of toolkits. All right? So a different take on machine learning for those of you that want some light reading. All right. So why did I show you all this junk? Well, remember that trees are constructed based on a gain metric, and that gain metric is conditioned on entropy. So let's do an example, a worked example. We have a training set, which is consisting of ones and zeros. How should we split it? What's our root of our tree? What should we split first? Well, let's consider a couple of choices. Okay, we could draw a vertical line here. Now, why did I say vertical? Well, remember that decision stumps and decision trees, they're splitting on an attribute. That means they're always on an axis. So it's just a line perpendicular to some axis or other. So it's always going to be a vertical or a horizontal line. Decision trees do not do this. No, sir. What they can do is you can fit a bunch of different branches in the tree, and you can do this. Right? And you can approximate a diagonal that way with a stair step. But it's not the same thing. All decision boundaries in a tree are going to be parallel or perpendicular to axes. All right, so we're going to try this vertical line first. What happens when we split that way? Well, we get this little thing off on the left and a bunch more on the right. Okay, let's consider another possible split. I'm going to draw a horizontal line here, and we get 3 and 3, right? Stuff on the top, stuff on the bottom. And finally, we're going to consider this split, which has a 4 and 2 structure. Okay, let's work the numbers. So remember, here we go. This is our thing we're maximizing. It's that gain term, which has got the entropy of all of this junk, okay, minus a bunch of terms for each split. So the entropy, so it's going to be, all this junk is here, that's S coming in, and then we're going to have to sum up over this entropy plus that entropy. Okay, that's how we're going to work that. Let's do the nitty-gritty. So for tree number 1 there on the left, what do we see? Well, what we have is one unit over here, and it's just one class. Okay, so the probability of class, I can't remember what that is, I guess that's probably class 0. So the probability of class 0 is 1, and so it's 1 log 1 is what we get over there on the left hand side. On the right hand side, that's still on the left hand side. So then what's the other class? Is there any probability of anything on class 1? No, sir. So there is a probability 0 of getting any class 1s over there, and of course it's the same thing inside the log. Now here is a problem. As you may know, the log of 0, that was not supposed to be a theta, that was supposed to be a 0. The log of 0 is undefined because you can't raise something to the power and get 0. That just doesn't happen. So we have to essentially end up with a convention here. And the convention for information and entropy is that this situation with probability 0, that's just going to go to a 0. That's not true generally mathematically, just to highlight that. Okay, so that is the left-hand side. So the right-hand side here, we're going to get the fact that, so note that we had those S terms on the front, remember that? So the S terms, there is 1 out of our 6 goes over on the left-hand side. On the right-hand side, we get 5 out of 6. So that goes there. We have, so 4/10 or 2/5 are this class, and 6/10 or 3/5 is the other class. And you work those numbers, you get 0.81. So the total gain is going to be the entropy of S of the original set before we split it minus 0.81, right? Okay, let's continue on. We're going to do that again. So for this guy, the left-hand side is 1/3 that and 2/3 that. So there's your 1/3 and your 2/3. And you see here there are 3 out of the 6 that go on that side. Okay, end up with 0.46. On the right-hand side, we end up with the same thing. It's just that the 2/3 is for class 0 and the 1/3 is for class 1. Okay, but we get to the same entropy because it's a 2/3, 1/3 split. That's what defines the entropy, not which classes it is. All right, so 0.46 plus 0.46 is 0.92, and that's what we get out of that one. So the last one I'm not going to work, but it's 75% one class, 25% the other, and then this one is all one class over here, so we get another 0 on the right. But that works out to h of s minus 0.54. So which one of these maximizes this gain function, right? Here's our gain function. Which one of these is the maximum? So I'm not even going to bother to calculate h of s. The entropy of the original set, we could do it, but we don't care because, these are identical across all of these splits. They all start off from the same root. So all we need to look at is which one of these minus terms is the smallest minus term. That is, it reduces the original entropy the smallest amount. that's going to be my maximum. Okay, so it turns out, lo and behold, that it is number 3. And you can look and see, why is number 3 the most informative? Why does it reduce surprise the most? Well, one of these is pure, it's all one class, and the other one is 75% the other class. So this is a very low misclassification rate. It's only a 25% misclassification rate over here, right? And this one is a 0% misclassification rate. So by splitting that way, we have reduced surprise tremendously. We are no longer so uncertain about what the right answer is. Okay, so final little bit here is that I want to go through 2 other algorithms quickly. So what I just did was fundamentally ID3. That was that first kind of Quinlan method of calculating decision trees. So there's a further refinement to the ID3 story, which is fundamentally about adding in the ability to do continuous things, okay? These orange highlights are the things that are different in 4.5, C4.5 versus ID3. So it can handle missing attributes mostly by ignoring them when it computes the functions, and it can prune the tree after it's built to try to reduce overfitting. It can remove leaves that are just overfit to noise in the training data. And we'll talk about that in a second. But the other thing that it does is that it uses a different kind of maximizer. It's now maximizing the gain ratio, not just the gain. So that same gain function is here in G, but now we divide it by a normalizer that's about the information coming in from the top, okay? So those are both done to make the trees work better, and especially work better with continuous features. Right, I'm not going to get into the nitty-gritty. Suffice it to say that one of the important factors in making good decision trees is to prevent them from overfitting. So once you get a fully built tree, some parts of it may be bogus. It may just be noise in the data that's being fit there. So one way to deal with that is, after the tree is built, you can remove whole branches of that tree, okay? And the way you can make that decision about what branches to remove is to have a criteria like this one, where what we're saying is that, so this R function is the misclassification rate at a leaf, okay? So there's a number of terminal nodes T, that's this term here, and there's the misclassification rate at each one of those terminal nodes. And if we want to decide whether to get rid of one of these leaves, one of these terminal nodes, right, then we just have to essentially fit an alpha, which tells us how much we want to trim node size, right? This alpha works a lot like our lambda function on an L2 norm, okay? So that lambda, when it's high, or that alpha when it's high, it wants to squish the tree or squish the weights and make it smaller, right? And effectively what this whole system does is it sets a threshold, which is a function of the misclassification rates of each of those nodes, and any node that has a misclassification rate greater than that is going to get trimmed off. Okay. So it's going to trim off these excessive nodes here, right? And we're going to get to this version of it, because maybe that's just noise, that last step of the tree. Okay, a few things about decision trees. There's some nice rules of thumb. If you would like to make certain that you have a good classifier, you're probably going to prefer a shallow tree. Why is that? Because the deeper tree may be overfitting. The more deep you go, the more you can take individual data points and assign them truth. And we all know that individual data points may be corrupted by noise and they may not be truth, right? So, yeah. Oh, this is a terrible animation. I'm sorry. We don't like that. We prefer the simpler tree generally. For all else being equal, right? For an equal misclassification rate, we would use Occam's razor and we would prefer the simpler tree. Okay. So for, if at all possible, we would like to have a balanced tree, right? So a tree which has equal numbers of nodes on the left and the right. A tree which is unbalanced like this may be more prone to overfit the data. Okay, so last couple of slides. One more of these algorithms that is common is called CART, which stands for Classification and Regression Trees. And its superpower is that we can do both classification and regression. Imagine that with a title like that, right? So we can do regression with trees, not just classification. It's fairly cool. The big difference here is that we split now on the Gini impurity, which is not information, but it's not far off, right? It's not p times log, so just to refresh your memory, right? Entropy of a particular variable x is going to be, sorry, I should write it like that, is negative p of x log p of x. Oh, I wrote that behind my head. Good job, Jason. Well, so here you'll note we don't have log p of x. Instead, we have 1 minus p. Right? So it's a related measure. It has a similar kind of shape to it. And in fact, it has such a similar shape, when you look at it like this, you start to see something. Okay, what's going on here? This is entropy. But if we rescale entropy to half and put it down here, then we can see that the Gini coefficient in the dotted line is very similar. Not quite identical. It's not quite as, it's got a steeper curve to it, right? So the Gini measure and entropy, though, have very similar shapes. The misclassification error, on the other hand, well, so it's convex, but it's, yeah, it's got big flat spots on it, right? I mean, it is a flat spot, the whole thing. So the misclassification error is a little different than Gini and entropy. And what does that mean? Well, this is why we don't fit trees on misclassification error, right? So if we have a parent node, which falls here, and it splits into two children nodes, that one of which has a lower and one of which has a higher entropy, then the average between them, which is fundamentally what we're calculating in an entropy calculation, is the average, is just going to be the same as the parent. We're going to end up back there at the parent. Okay? So the entropy gain is going to be 0 in a misclassification setup. That's no good, right? If we get an entropy gain of 0, we're not going to do anything. We're not going to keep splitting. So if you look at Gini and entropy curves, right? So here's our parent node, and it gets two children nodes. Well, because this is a convex function, this is a chord. And that means that the average between those is, by definition, lower, right? I know I'm drawing it very poorly, and I apologize for that. But so the child node and the parent node have higher and lower, and that means the average of the entropies is over here, because this is a chord, and that number is a lower entropy or a lower Gini impurity, and therefore we're going to keep splitting. We're going to get a gain, and we're going to keep going. All right, so it doesn't matter whether we use Gini or entropy. They have very similar shapes, and their shapes being convex, that is what allows them to continue to split. Whereas if we used misclassification error, that wouldn't happen. All right, so how does CART work for regression? Well, it's about as dead dog simple as you can imagine. For every split, we are defining a location here. So each one of these is a split in the tree, right? So this is a leaf, represents this value of x between 0 and 0.5 or whatever. This is one leaf on the tree. And between 0.5 and 1.2 or whatever that is, that's another leaf on the tree. And all a CART regression is for every data sample, those yellow dots that's in the training data, every yellow sample that's within that leaf, just take the mean, and we're going to guess the mean of that. So here, we guess that value. Well, actually, sorry, looks like I did this wrong. Oh, these are two different trees, that's why. So blue is the tree I was drawing, right? So this is the mean for the max depth of 2 for a tree that's only going this deep, right? And the other one is a max depth of 5, so it keeps on going. So that's the mean of everything in the leaf on the 2 deep, and this is the mean of everything on the 2 deep. So it looks like it goes there is that leaf, and then that leaf. Okay, so you can see that we just guess a bunch of straight lines, and we tile up the space with a bunch of straight horizontal lines, and that's what we're learning. Okay, so it's a very simple kind of digitized version of any given curve. It's going to fit as many leaves as it needs to, and we can control the overfitting with this pruning methods. Okay, that's the end of decision trees. We've reached it here 2 years later. The decision tree classifier is easy to implement in sklearn. You'll note that you have arguments like whether you want to use a splitting function on Gini or entropy. You have options like what the alpha is going to be there to do some post pruning. Okay, and just implement and go, because as you can see, this is the kind of thing that you don't want to implement. It's rather annoying. And when you look at decision boundaries learned that way, you can see once again that they're all square decision boundaries. They're always parallel, perpendicular, or perpendicular to an axis. Okay, they're very widely used, these kinds of things, especially in their iterations with more and more fancy stuff on top of them, like random forests or XGBoost. Okay. The key really is that it's a divide and conquer sorting kind of algorithm in the end. And like k-nearest neighbors, and in fact, when you look at CART, you should be thinking k-nearest neighbors, right? CART is just like k-nearest neighbors for regression. We just find all the things in our neighborhood, right, with CART, and we just find everything that's close by, and we guess the mean of everything that's close by, or we guess the class of everything that's close by. So, all right, so like k-nearest neighbors, what I was saying is that it has incredible power. You can fit just about any kind of decision boundary, no matter how complex. But the algorithm itself is very, very simple. Okay? If you can have a method to prevent it from overfitting the crap out of itself, these can be surprisingly good, and they will work on almost every problem that can be worked on. Okay? Again, caveat being, don't overfit. All right. Thank you so much for listening. I know that this has kind of gone on a bit extra, so I'm going to split it into 2 separate lectures, but hey, that's the way the cookie crumbles. All right. Have fun, everybody. Bye.